All right, so today we're going to begin our two-parter on time series. Today we're just going to take a look at time series data, but then on Monday, our next study group, we're going to look at time series models. Before we get into time series data, just like as a preface to the models, there are a group of traditional time series models, and those are the ones that we're going to talk about on Monday. They're all linear models, so we'll be seeing things that are very, very similar to the outputs that we saw when we were doing linear regression. So just as a preface to that, that's what we're going to expect. Now, there are methods that you can build upon these traditional time series models. For example, I mean, as a big jump, you can even do neural networks on time series data. And when we get to neural networks, I'll mention just really briefly how that is done. And between the two extremes of traditional linear models as well as neural network models, there's a lot of possibilities in between. So with this curriculum, there are these linear models that we're going to talk about on Monday. But then, other than that, in the appendix, again, if you're interested in time series, highly recommend going through the appendix for time series. There are only 2 additional lessons, one of which is another linear model, and the other is actually a model that is built by Facebook. It's in a different library, but it is sort of like the traditional time series models, but a little bit of a twist. Not a twist, but it's a little bit more complex. So with that, any questions or thoughts on that structure? Cool. Well, let's get started then. Again, today we're just going to be talking about patterns to look out for when you're dealing with time series data. So what is time series data? It is a series of values of some quantity obtained at successive times, often with equal intervals between them. For example, we have the temperature of July recorded daily, average weekly price of a stock in the past year, and average annual government budget in the past 30 years. So here the values, or the periods here we're talking about. Here we have daily, this is weekly, and then this is yearly. But all of these, because they're measured in time, this is all time series data. One other thing to mention is we're going to focus on univariate time series, which records a single observational variable at different but equal time intervals. Univariate time series just means that one of our variables is changing with time. There's multivariate time series, for example, if you want to predict a price of S&P stock, S&P is not a stock, the price of S&P, but you also perhaps want to use the price of, I don't know, the current price of gold. That becomes a multivariate time series because those are 2 things that are changing with time. So yeah, with multivariate time series, unfortunately, with traditional models, that is not covered in this curriculum, but it is pretty easy to implement with a neural network. But we'll see that when we get there. So now that we know a little bit about time series data, what are some characteristics? The most notable characteristics in time series data are patterns that could emerge, specifically trends and seasonality. Your lessons go way more in depth into these patterns, but just wanted to point out a couple of things. Trend, is there an overall upward trend, overall downward trend? Does it stay mainly flat? And also seasonality. Are there, recurring patterns in your data? Do you notice that the temperature gets warmer midday and then colder at night? Then you'll have daily seasonality. Do you find that, the stock price goes down in December and then up again in the summer? That would be yearly seasonality. And those are things that you want to take note of when you're doing your EDA for your time series data. Beyond that, an important pattern in time series that occurs is stationarity, which is an assumption that lays the foundations for time series forecasting and modeling. For the models for the models on Monday that we're going to talk about, works best if you can get your data to be stationary. And we'll talk a little bit about stationary data. So the main things to look out for characteristics of stationary data is first that it has a constant mean, but also has a constant variance. So constant mean, you don't want any overall trends, and we'll later talk about ways to correct for these trends. And then also constant variance. If you remember, we had this issue when we were dealing with linear regression, homoscedasticity, if anyone remembers that word. Homoscedasticity just means constant variance as well. Reasons why we don't want to have heteroscedasticity or non-constant variance is because you have variable predictive power at different points of your data. So for example, if you have this non-stationary series and you build a model assuming that the variance is constant, let me just draw some lines over here. Let's say that this blue line is the mean, and the average variance, if I average the variance throughout, you can sort of say that the variance on average is maybe between like this green line and then this green line. With that, where you're making predictions in the future, when you have bigger peaks and troughs like this, you will lose predictive power, and that's something that you don't want to have in your model. You want your model to be as consistent as possible. And we'll talk about ways we can get rid of heteroscedasticity as well. Any questions so far? Oh, and also covariance. But covariance is a little harder to check for. But yeah, any questions at this point? All right, so these are really easy things to check for. One, plot a line graph of your time series data, see what it looks like. In a little bit, we'll also talk about a statistical test that you can just run, and it'll tell you if your data is sufficiently stationary or not. All right, so why does data need to be stationary for modeling? Well, it's important because without it, a model that is describing the data will vary in accuracy at different time points. Exactly what I was saying earlier. You lose predictive power if you don't account for changing variances. Stationarity also kind of lays the foundations of typical time series models, and this is what I mean by the traditional time series models. We'll see all of these tomorrow. AR models, which stands for autoregressive models, MA, which stands for moving average models, and ARMA stands for autoregressive moving average models. So a violation of stationarity can cause problems in prediction. So a couple ways to test for stationarity. One, just examine the visualization, just plot that line graph and see what it looks like. Is it going upwards? Does it have these uneven variances? Stuff like that. We can also look at summary statistics, like I said, mean, variance, covariance, if any. And also this is the statistical test that I'll share in a little bit. I hope I have this CSV here. Hold on. Let me just make sure I have the CSV before I run into an error. But yeah, any questions at this point since I'm doing this?
Yeah, I have one. So you're talking about sufficient stationarity. So basically, you mean there's just some sort of variance, like the temperature goes up in the summer and down in the winter, where I live. So of course, there's going to be some variance in those. If you look at the chart, it's not going to be exactly even. It's not going to be a perfect sine, but that's fine as long as it's like within a certain range. That's what you mean?
That's right. Yeah. And with that range, it's the easiest to confirm with this statistical test that we're going to talk about in a little bit. All you have to do is make sure the p-value is below 0.5 and then 0.05, sorry. And then you can just say it's sufficiently stationary. But yeah, that's exactly right. It's almost impossible to have perfectly stationary data. So for this notebook and for the next one as well, we're going to use this very, very simple shampoo data set, which is the sales of shampoo, I think over 3 years. Yeah, the monthly sales of shampoo over a 3-year period. So here you can see there are only 36 data points. And this is collected monthly, and it's basically the sales of shampoo over 36 months. So based on this, we can already say that is not stationary. We already see a very obvious upward trend, and all of these zigzags going up and down show that, the fact that there are different magnitudes of going up and down show that there is not a constant variance. To further confirm that, we can take a look at our summary statistics. So here, what we're doing here, one way to check for, all right, is the mean and variance constant? Here, I'm just dividing this data set into two. So here there are 36 points. What I'm doing here is I'm splitting it into 18 and 18 points and just comparing the mean and variances of those two sections. So in the first half of the data, the mean is about 200. Sorry, let me make this a little bit bigger. In the second half, the mean's around 400. So that's already a violation of stationarity. And the variance, you can see at the start, about a 3,300 variance, and at the end, 17,000 variance. So obviously, we don't have a stationary data set over here. So these two are simplistic ways to go about it, but typically in your projects, if you do decide to do time series, you're going to use the DigiFiller test. So the DigiFiller test is a statistical test for testing stationarity. The null hypothesis is that the time series is not stationary. So if the test statistic is less than the critical value, we're going to reject the null hypothesis and say that it is stationary. So basically, low p-value is better. The DigiFiller test is available in stats tools from the stats models module. So actually, I don't have it in this notebook, but I do have it in Monday. So let me just pull it up really quick. We're going to go over this notebook then, but just to show you all what the DigiFiller test looks like, let me just quickly run this and look for the DigiFiller test. There we go. So here, the DigiFiller test comes from stats models, which we're familiar with from linear regression. It's called DigiFiller, and all you have to do is wrap the values of your data into DigiFiller, and it will be able to show you this. Hopefully, yeah, I'm not missing anything. But right now, you can see that this is the same data set. The DigiFiller test gives you a p-value of 1. So it's definitely not stationary. Yeah. Any questions about
one quick question. So now let's say if we run this test and like if the p-value is less than 5 as we want, so does that mean that it is, I mean, is it as a definite mean that okay, it's stationary, the data, or it still can be?
Yeah.
Because we are going for null hypothesis as variable.
Yeah.
I'm talking about changing.
Yeah. If you have a p-value below 5%, it's stationary enough.
Okay.
Yeah, you can probably never find a perfectly stationary data set, but yeah, as long as it's a p-value of below 0.5, it'll be stationary enough. We'll probably come back to this to see what the next thing I'm going to talk about. So, all right.
It will be 0.05, right?
That's right. It'll be 0.05.
Yeah. Okay.
Yeah. All right. So there are some things that we can do to stationarize our data, also known as removing trends. There's a link to a series of other ways of removing trends. But the main way that we do this is by taking differences of the variable over time. And this is known as differencing. So as some quick terminology, so what lag is, for some specific point t, the observed t minus 1 point, so basically yesterday's price, is the ith lag, is the one lag of today. So basically today, if today's my price is 100, yesterday my price was 96, the one period lag of today is 96. So basically yesterday's price. So differencing, basically what it does, it removes our data's dependence on time. It's really just performed by subtracting the previous observation from the current observation. So really what differencing is doing is your new values will just be the change in your values. And you'll see that typically it leads to flatter and flatter curves overall. So as a quick example, so the difference here is just today's observation minus the day before's observation. So as a really quick question, if we have a time series data set that literally goes up in a straight line, in 10 days in a row, it goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, price increases by 1 every single day, and we want to difference by lag equals to 1, what would the result be? Any guesses or ideas? No, nobody?
Don't we require the data which is beyond this 10?
Well, you can get the difference of any data point. So basically, the difference data here on day 2 is just going to be 2 minus 1. The difference for this day is going to be 3 minus 2. So basically, it's kind of similar. I know this may or may not help some of you, but it's a very similar concept to taking a derivative, but not exactly. But basically, with this data set that goes up in a straight line diagonally from the price of 1 to 10 over 10 days, the difference data will just be a horizontal line flat at 1, because every day the increment is 1. This is just a function that is doing differencing manually. There is a built-in function. I have it over here, but you can see here that if I do the value that I'm doing here is the data set at I minus the data set of I minus the interval, however many times you want to do the lag. So we can use this function and we can do difference of our list of 1 through 10. Let me actually just copy and paste this so it'll be quicker. By doing this, you can see our difference data comes out as all 1s. One more thing to note is when you difference your data, you do lose a couple data points depending on how much lag you have. So you can see here that there are only 9 data points, and that's just because you cannot take the difference of the first data point that you have. So that's just something to take note of. Any questions at this point?
So is this function going to be a standard function?
There is a built-in function that I actually have in the next cell. It's just .diff. So if I do like instead of this, and I wonder if it'll work if it's just a regular list. It has to be a series, I think. Maybe a data frame. Let's see. There we go. If I do this, I use the .diff, which actually comes from pandas. I will get a list of 1s, and as I mentioned before, the first one is a null value.
So will there be a requirement of this function to be written because both are giving me the same results?
Oh yeah, no, you definitely do not. You don't have to write this. Don't write this. This is just an example to show like how it works of what it's doing. All right. So as we can see here, we had like a line that's going diagonally up. Now we have a flat line. So essentially we've removed the trend in this data set. Of course, this is a very, very simplified data set. Let's see what this effect is on our shampoo data set. So here I have my shampoo data set. I'm calling the .diff. If we take a look at the difference observations, we can actually take out the .head. You can see that now we end up with a bunch of negative values as well, because whenever the previous day is higher than the current day, you get a negative value, which is fine. But we're going to do here, if we plot this data, you see that there is no obvious upward trend anymore. There is still a little bit of heteroscedasticity going on, but for the most part, we've gotten rid of the big upward trend. And this is just the difference data this is just a difference data, a different version of the data that we had before. So let me just do a quick dot plot so we can compare. There we go. Yeah, it went from an obvious upward to a flatter overall trend. So sometimes you actually have to difference your difference data. So if you imagine, and again, this is a math example, but if you have a quadratic function and you take the derivative of that, you end up with a straight line that is, sorry, a slope, and then you would have to do another level of differencing to get it to be flat. So you can difference your difference data. That is definitely a possibility. If you see that after one differencing, your data is still, having a slight upward trend, you might want to difference again. Of course, what you can do is you just take this data set and run it through the DigiFiller test to see if it's differenced enough or not. So I think I do have an example here. So I'm going to take the difference data here, the DigiFiller difference data here, and then run it through the DigiFiller test. And you can see right now the p-value is already small enough just by doing one level of differencing. So yeah, the p-value goes down to like 0.1001. So we're good at this point. So this data is now stationary enough to be used in the models that we'll talk about on Monday.
So now if I keep on, let's say, now I give a variable, right? And say that, okay, this variable one is the difference of, right, the shampoo, right? And then I say that, okay, variable 2 is the difference of variable 1.
Okay.
That's how are we going to reduce the, change the difference? Like take the difference of the difference? The same.
Sure. So I can do this. Hopefully this works. I think this should be able to stack, but let me just see. Does it say float argument must be a string? Okay, let me just replot that again. So if I do shampoo.diff, this is what we get. If I .diff again, oops, what do we got here? Yeah, if I difference it one more time, this is what we get. And I can do a dot plot of this. And I mean, it ends up looking different. If you take a look at the, yeah, this is difference twice. This is difference once.
And there is no limitation on.
Oh yeah, you can difference as many times as you want, but I mean the marginal value of differencing another time is going to get less and less. So doesn't, yeah. If you difference one time and you see that your DigiFiller test is still giving you a p-value above 0.05, then difference another time and see if that helps.
And when you run the model, are you going to run it on the difference data or the actual data?
That's a good question. It depends on what model specifically you're running. So some models have a difference component embedded in the model. So you really only need to tell it that you can feed in your raw data and say that, all right, through my EDA, I found out that you only need to difference it one time or maybe two times. And then you tell your model that your model will do it for you. And then
it'll be run on the difference data. Either that's embedded, could be built as part of the model, but it's still the difference data it's using in the end.
Yep, that's right.
Does it kind of consider it though the same? I mean, like, couldn't you make the argument that, oh, this is totally different data? How can you use this for a model? Now you've made all this transformation to it.
So the perk of, so typically if you want to introduce differencing in your model, or if differencing is something that your data has to go through to become stationary, you would end up using a model that has a difference component. Just because when you're coming up with predictions, they will undifference it for you.
Oh, okay.
If that makes sense. Yeah. Versus if you're doing the differencing manually, and then if you just throw it into a model that doesn't have that differencing component, you would have to manually undifference it. Yeah. Which is basically, you would have to add back the differences over time.
Okay.
And yeah, people don't do that typically. And I will tell you all now that most models in time series probably have some differencing component.
So is this the reason,
sorry, say that again?
Is this the reason that the k nearest neighbor works the best?
I don't think so. You have a more specific example? Like k nearest neighbors working best for like your last project?
No, and now let's say if we have, because we are getting the data into stationary mode, right? The data points will probably like come closer and closer.
That's true, yeah.
Yeah, and that's right. I mean, I'm just picturizing it. I'm not really
Okay.
sure how that works. But then one of the documents said that right, for time series, most of the times people use k nearest neighbor.
Oh, interesting. So, okay. I think those are two different things. So time series, yes, we have these models. You can also take out the time component of your data and just treat them as just individual observations, and they could work well with k nearest neighbors. And the idea of that is, you know, if you have a bunch of similar things happening, it's likely to be around the same period of time. Whether these two things are like affecting each other um, on um, on this level that we will talk about, no. And whether it does on a deeper level, I'm not too sure either.
We'll figure it out.
Yeah, we'll figure it out. But yeah, any other questions about differencing? All right, well, if you keep differencing your data will start to look more and more like a flat line. That's just how differencing works. The differences between your differences are going to converge to 0 over time. That's just something to know. All right, so once we've achieved stationarity, the next step is fitting a model, and the next overall thing we're going to look for is autocorrelation. And we'll talk about autocorrelation for the rest of this notebook. Time series usually exhibits two kinds of behaviors. So first, you can predict a value in time series using a past value or values. So for example, if let's say, oh wait, I'll get into that after we talk about autocorrelation. So what exactly is correlation? Is autocorrelation? Autocorrelation is the correlation between the time series data and the same time series but shifted by a certain number of periods. So for example, if I want to look at the prices from Monday to Friday, I want to see if they are highly correlated to the prices one lag time back. So Monday to Friday, I'll compare it to Sunday through Thursday and take a look and see, is that correlated with itself? So there are a couple visualizations for that. So first, you can actually shift your time series using the dot shift method. So you can see here, and let me actually just do this. You can see that by shifting, all it does is it moves it one step down. I end up with a NaN value here. I end up with a NaN value there, but that's fine. Basically, we want to see if these two are correlated. We can literally run like a df.core and see that these two time periods are correlated by 0.7, with a correlation coefficient of about 0.72. But yeah, this is what it looks like on a graph. If I want to see it with 2 lag times, this is what it looks like. I can even add shampoo sales lag 2 in here. And see that, all right, between the regular time series and shifted by 2, it actually has a correlation of 0.85. So what this is saying is that using the data from 2 days back could be very helpful as a predicting factor for today, if that makes sense. Going into some of the more proper visualizations, we have 2 charts that we look at, the ACF, autocorrelation function, and PACF, partial autocorrelation function. So
Sarah, could you go back up for a second?
Yeah, up to where?
To there. So when you shifted one day, it was 7.72, and 2 days it was 0.85. So is there a particular reason why it got better after shifting 2 days, or is that just coincidence of the data?
Coincidence of the data. I will say most of the time it is like a decreasing correlation over time, but with this data set, I guess it just so happens that, yeah, second one is way more correlated. Yeah, but that's a good observation. So yeah, back to these. Both of these graphs are within stats models, and they can be a little bit confusing to interpret at the start. So let's take a look. So these are what ACF graphs look like. It's literally plotting the correlation coefficient between the original time series and future lags. So as you can see here, this pattern is exactly what we observed earlier, right? This point is around 0.72, or what was it? Let's see, this is 0.72 and then goes to 0.85. Here we have around, yeah, it looks like it's around 0.72. Maybe not, this doesn't look like 0.85, but you can see that it goes down then up again. It's probably because I have the NAND values that's adjusting it a little bit, but same idea. It's a very, very common pattern to see. And actually this is plotting out twice because I don't have the plot.show. Oh, shoot. Did dot show? Never mind. We're not going to bother with that right now. Okay.
You did PLT and not plot, I think.
Okay. Never mind.
Vice
Yeah, I also don't think I have matplotlib here. Anyways, I'm not going to harp on that. So yeah, it's a very, very common pattern to see that autocorrelation is slowly going to get less and less over time. Because you imagine if there's a trend that is continuing, the more time you look forward, the less that trend stands, if that makes sense. So autocorrelation, we can see here, it looks like the first 4 lags have some pretty strong autocorrelation. Note this for future model building. So this is something that you will take note of. And obviously, as we can see here, autocorrelation does propagate down to other lags. The influence of a strong autocorrelation causes additional lags to be highly autocorrelated. So something that we use in conjunction with this is PACF to discover the true relationship between lags. So PACF, and we'll plot this graph and see how different it looks. This is what a PACF graph looks like. So partial autocorrelation looks at correlation between a point and a particular lag without the influence of intermediary lags. So this helps us see the direct relationship between certain lags. So it does seem from this plot that the first 2 do have strong autocorrelation. We can safely now say that, all right, this second point here has a correlation of like about 0.5, discounting the fact that the first lag was highly correlated. So because, you know, there is the common trend of lags of autocorrelation propagating, the partial autocorrelation sort of discounts previous lags and basically discounts the fact that, all right, how much of this lag is a result of autocorrelation from previous time lags that has propagated down. So PACF is also something that you look out for. And usually what you look for is like anything that is outside of this boundary. So here we can say that, all right, we'll just take note that for partial autocorrelation, the next 2 lags still have strong partial autocorrelation. And that's just something that you'll take note for our models that we'll talk about on Monday. But yeah, this is really all that is. I will say that this is the harder part, or more of the newer stuff from section 37 on time series data. The rest of the stuff in this section is working with new pandas methods, working with some of the different built-in methods within pandas that are meant to be used with time series data. So it's really just a bunch of different new methods that we haven't used before. So highly recommend just like going through just to have some familiarity with what exists, so that you don't try and like, you know, hard code a method that doesn't need to be hard coded. But yeah, I think yeah, a couple of you have already gone through this material and you have been saying that it's not too complicated. But yeah, at this point, any questions?
I have a couple, I think.
Yeah.
So what does the blue region mean again in those charts?
So the blue region, it's sort of, you can sort of think of it as like, it's a similar concept to like a rejection region, but it's basically the region where like the threshold for which correlation you want to take note of. So anything that is outside of this region is considered significant. So the first 2 here, if you want to get even more complicated, you can even say, all right, the 16th seems to have like a very strong negative correlation. And then it's really up to you to decide like how you want to deal with these that are near the boundary, but usually you start at the top. Same for the autocorrelation plot. You can see that the first 1, 2, 3 happen to be outside the blue, the transparent blue area. Again, you can interpret that as like what is significantly correlated.
So, I mean, for the data, do you want it correlated or not? What's for the models?
For the models, you are going to, basically in the models, you're going to make use of autocorrelation to help in your prediction. So basically saying that, my first 2 lags have strong autocorrelation is just going to say that in making future predictions, I'm going to use the prices from the last 2 days to help to aid in my prediction. And that is something that you do feed into your model that we'll talk about on Monday.
Okay.
Yeah. So for example, like this is actually one of the hyperparameters that we'll see, the number of like autocorrelation terms to include. And based on this, we would include 2 autocorrelation terms in our model. And that is a hyperparameter that you tune, or that a hyperparameter that you give your model.
Okay.
Yush, why have you used -1 on?
I use -1 because the last one I think is
A null value?
Yeah, I think it's because the last one is a null value. I wonder what happened if I don't have the -1. Yeah, I think it's because of the null value. Yeah, so let's see. Yeah, let me take a look at what that shampoo data set is doing. Yeah, the last one happens to be a null value. Yep. Anything else? All right. I will say time series for a subset of people is very, very straightforward. For another subset of people, it is not. I will admit that like when I was first learning this, it took me a long time to grasp like the concepts of time series. So if you fall under that category, we can discuss it at one-on-ones. So yeah, if there are no final questions.
One I just thought of.
Yeah.
On what stage do we start using this? And once we have completed, done modeling, or before modeling, or just to compare like pre-time series, what was the model predicting, and then again you do it post. How do we?
So this is
that?
all done before any time series modeling. So before you even start, right, you'll look at your data and say, all right, am I going to use traditional like regression? Am I going to use classification, or am I going to use time series models? And if your answer is you want to use time series models, then you have to do all of these steps before you even get into modeling.
So let's consider the project. Like now, let's say now if I write if it's the Zillow project for time series.
Yep.
Now, let's say if I'm just running my regular, all the modeling without the time series, and I'm still able to get certain prediction correct. In that case, do I just say that, okay, I create one book where all the predictions are like as per the previous one, and then to compare it, what I'll do is I'll just run a time series model.
Okay, I see where the confusion is. So for time series projects, for univariate time series projects, you're only going to have one column of data. We're going to use shampoo data from the past to predict shampoo data in the future. It's just one column. This is our, not this, but this is our entire data. There are no other features. There's no target. There are no X's. There's no like, it's just one column. So we're just using one column, and we're just kind of predict future values for that column. So you wouldn't be able to put this into a classification model or a regression model at this stage.
Okay, but then like, see, if there are multiple zip codes where they say that, okay, we want prediction for multiple zip codes. In that case, like each zip code probably becomes one feature.
Yes, if you want to use the prices for other zip codes to predict one zip code. I know where the confusion is. It's because the project is set up in a way that, for those of you who haven't looked at it yet, the time series project for this phase is basically you're given a bunch of zip code data on like prices, like housing prices in each zip code over a period of time. And the prompt is to figure out what are the top 5 zip codes to invest in that will, like, basically are forecasted to have higher prices in the future. A typical workflow for this is you're actually going to create a model that you can use on each zip code, and it will likely be the same model on each zip code, or create a function that will tune a model, and you'll basically have different models per zip code. You're not going to do EDA for every single zip code that is in that data set, which is, I guess, why that is confusing. But yeah, you would treat each column or each zip code's data as a univariate time series project. That makes sense. When we get closer to the project, I will like dissect each project and say like, all right, this is what I'm expecting. This is like a suggested process.
Okay.
Anything else? All right, then. Well, on Monday, we're going to talk about time series models. Again, like all of the notebooks for time series, as well as the next couple on natural language processing, are up on the GitHub repo in case anyone wants to like explore in advance. All right. Well, this is all I had to share for you all today. If there's anything else, as usual, please let me know. But if there's nothing else, have a good night, everybody, and I'll talk to you all soon. Bye.
Good night.
All right.